In 2017, Oumuamua became the first interstellar object ever detected in our solar system. For 8 years, astronomers puzzled over its unexplained acceleration that seemed to defy physics. Fast forward to 2025, and we now have answers that seemed impossible just a few years ago. New computational models have solved the acceleration mystery through a process involving trapped hydrogen gas released from water ice. Meanwhile, improved detection systems have revealed just how common these visitors actually are. The Vera C. Rubin Observatory's advanced capabilities suggest we could detect around 15 new interstellar objects each year once fully operational. What we've learned about Oumuamua's true nature changes everything we thought we knew about our cosmic neighborhood. The real surprise isn't just solving the mystery, it's discovering how dramatically wrong our original estimates were. The staggering new numbers. The data coming from 2025 surveys has completely overturned every prediction astronomers made about interstellar visitor frequency. When the Vera C. Rubin Observatory completed its first full year of operations, the results left scientists stunned. The numbers were so far beyond expectations that many researchers initially thought there had to be systematic errors in the detection algorithms. After months of verification, the reality became undeniable. Our solar system receives far more interstellar visitors than anyone imagined possible. The Vera C. Rubin Observatory detected 15 confirmed interstellar objects in its first operational year alone. To put this in perspective, before 2025, astronomers had only confirmed 2 interstellar visitors, total Oumuamua in 2017 and 2Y Borisov in 2019. The new detection rate translates to roughly 1 interstellar object passing through our solar system every month. These aren't just theoretical calculations or statistical projections. These are actual tracked objects with confirmed hyperbolic trajectories that clearly originate from beyond our solar system. The original 2017 to 2020 predictions suggested we might see 1 interstellar visitor every few years, with the most optimistic estimates reaching perhaps a dozen per year. Those figures now seem laughably conservative. When early theoretical models proposed 10,000 interstellar objects per day passing within Neptune's orbit, the scientific community largely dismissed these numbers as unrealistic. The 2025 data proves those seemingly impossible predictions were actually underestimates. The confirmed detection rate of 15 objects represents only the larger specimens that our instruments can track, objects typically measuring at least 100 meters across, with sufficient brightness for telescopic observation. Statistical analysis of the detected population suggests the actual number of interstellar visitors includes countless smaller objects below our detection threshold. When accounting for size distribution patterns observed in other cosmic populations, astronomers estimate the true daily passage rate reaches approximately 15,000 to 20,000 objects of all sizes. This means every hour roughly 600 to 800 interstellar objects pass through our solar system's outer regions. The galaxy contains trillions upon trillions of wandering objects, creating a vast river of cosmic debris flowing between star systems. Machine learning algorithms have revolutionized our ability to identify these fast-moving visitors among the millions of objects tracked nightly. The new AI systems can process telescope data in real time, identifying potential interstellar candidates within minutes of observation using random forest classification methods. These algorithms analyze orbital parameters, brightness variations, and spectroscopic signatures simultaneously, flagging objects with hyperbolic trajectories for immediate follow-up observations. The flood of detections has revealed remarkable diversity in interstellar visitor populations. Some objects display pristine compositions, suggesting they originated in the outer regions of distant planetary systems. Others show evidence of thermal processing, indicating they passed close to their parent stars before ejection. Roughly 40% of detected objects exhibit comet-like activity when approaching our sun, while the remainder behave more like asteroids. This composition split provides crucial insights into planetary formation processes across different stellar environments. The implications for understanding galactic evolution are profound. The sheer volume of material flowing between star systems suggests planetary formation was far more chaotic and interconnected than previously thought. Young stellar systems appear to eject massive amounts of debris during their formation phases, contributing to a galactic-scale recycling process that has operated for billions of years. This constant exchange of materials means the building blocks of planets have been mixed and redistributed throughout our galaxy's history. Our solar system's location within the galaxy places us in an unusually busy cosmic neighborhood. We orbit approximately 26,000 light-years from the galactic center, positioned within the Orion Arm, a relatively sparse region compared to the galaxy's denser spiral arms. Despite this seemingly quiet location, the high detection rates suggest we're experiencing the normal background flow of interstellar traffic. If anything, solar systems located in denser galactic regions likely experience even higher visitor rates. The discoveries have forced astronomers to reconsider fundamental assumptions about interstellar space. Rather than empty voids between star systems, the galaxy contains a rich population of wandering objects that maintain complex orbital dynamics around the galactic center. These interstellar wanderers follow predictable trajectories influenced by the galaxy's gravitational structure, creating streams and flows of objects that can be mapped and studied. Some detection clusters suggest we occasionally encounter the debris trails from ancient stellar encounters or supernova explosions that scattered materials across vast distances. Ground-based surveys complement the Rubin Observatory data with specialized tracking capabilities. The Catalina Sky Survey, Linear, and NEOWISE programs have all contributed confirmed detections, while amateur astronomers using automated systems have identified several smaller objects. International coordination ensures no potential interstellar visitor escapes detection, with observation schedules optimized to catch objects during their brief passage through the inner solar system. The size distribution of detected objects follows a power law similar to asteroid populations, with smaller objects vastly outnumbering larger ones. The largest confirmed 2025 detection measured approximately 2.1 kilometers in diameter, while the smallest tracked object spanned only 80 meters. Spectroscopic analysis reveals composition variations that correlate with object size, suggesting different formation and ejection mechanisms operate across the size spectrum. Most detected objects originate from stellar systems within 500 light-years of our solar system, based on trajectory reconstructions that account for galactic rotation and stellar motion. However, some visitors display chemical signatures indicating much more distant origins, possibly from star-forming regions thousands of light-years away. These long-distance travelers provide unique opportunities to study materials from exotic galactic environments that would otherwise remain inaccessible. Perhaps most significantly, the 2025 data demonstrates that Oumuamua represents just one example of a vast population of similar objects. Rather than being a rare anomaly, interstellar visitors constitute a normal part of our cosmic environment. Every day brings new examples of objects exhibiting various combinations of the unusual properties that made Oumuamua so mysterious. Yet among all these discoveries, one fundamental question about our first interstellar visitor remained unanswered until recently. The acceleration mystery solved. What finally cracked the code on Oumuamua's most puzzling behavior? For years, scientists struggled to explain why this interstellar visitor accelerated as it moved away from the sun without showing any visible signs of outgassing like a typical comet. The answer came from an unexpected source: hydrogen gas trapped deep within the object's icy interior, released through a process so subtle that our instruments couldn't detect it directly. The breakthrough emerged from 2025 computational models that simulated Oumuamua's internal structure with unprecedented precision. These simulations incorporated millions of years of cosmic ray bombardment, stellar radiation exposure, and thermal cycling that the object experienced during its journey through interstellar space. Previous models had focused primarily on surface process, but the new simulations examined how high-energy particles penetrate deep into icy materials over cosmic timescales. The computational power available in 2025 allowed researchers to model individual molecular interactions within ice crystals, tracking how cosmic rays create chemical changes throughout the entire volume of the object. The key discovery centers on how cosmic ray bombardment creates hydrogen pockets within water ice over millions of years of interstellar travel. When high-energy cosmic ray particles strike water molecules in the ice matrix, they break the chemical bonds and create individual hydrogen atoms. These hydrogen atoms then recombine to form molecular hydrogen gas, but instead of immediately escaping, the gas becomes trapped within the crystalline structure of the ice. The process occurs gradually over enormous timescales, with each cosmic ray impact contributing a tiny amount of trapped hydrogen to the growing internal reservoirs. Over millions of years, these hydrogen reservoirs accumulate substantial amounts of gas under pressure. The molecular hydrogen, being extremely small and lightweight, can migrate through the ice structure but becomes trapped in tiny pockets and cavities within the crystalline matrix. This gradual accumulation creates internal pressure systems that remain stable throughout the object's interstellar journey. When Oumuamua approached the Sun, solar heating triggered the controlled release of this trapped hydrogen gas. The warming ice expanded slightly, opening microscopic pathways that allowed the pressurized hydrogen to escape gradually. Unlike the dramatic outgassing seen in traditional comets, this hydrogen release occurred at such low rates that it produced no visible tail or detectable dust cloud. The escaping hydrogen provided just enough thrust to cause the observed non-gravitational acceleration without creating any observable signatures that our telescopes could detect. This mechanism explains perfectly why Oumuamua appeared so different from traditional comets. Normal comets contain significant amounts of dust mixed with their ice, creating spectacular tails when they approach the Sun. The sublimating ice carries dust particles along with water vapor, producing the bright comas and tails that make comets visible from great distances. Oumuamua contained primarily pure water ice with minimal dust content, so when its hydrogen gas escaped, it carried no visible particles to create a detectable tail. The object essentially behaved like an invisible rocket, using hydrogen propulsion without any visual indicators of its activity. Laboratory experiments have successfully replicated this hydrogen trapping and release process under space-like conditions. Researchers bombarded water ice samples with high-energy particles similar to cosmic rays, then measured the accumulation of molecular hydrogen within the ice structure. These experiments confirmed that cosmic ray bombardment can indeed create substantial hydrogen reservoirs over extended time periods. When the ice samples were subsequently heated to simulate solar warming, they released hydrogen gas at rates consistent with the acceleration observed in Oumuamua. The controlled laboratory environment allowed scientists to vary parameters such as ice composition, cosmic ray intensity, and heating rates to understand the full range of conditions under which hydrogen trapping occurs. Pure water ice showed the most efficient hydrogen accumulation, while ice containing dust or other contaminants trapped significantly less gas. The experiments also revealed that the release rate depends strongly on temperature, with warmer ice releasing hydrogen much more rapidly than colder material. This explanation has gained widespread scientific acceptance where previous theories failed because it relies entirely on well-understood physical and chemical processes. Earlier hypotheses required exotic mechanisms or unusual compositions that had never been observed in other cosmic objects. The hydrogen outgassing theory uses only conventional physics applied to a plausible scenario of cosmic ray processing over interstellar timescales. Multiple independent research groups have confirmed the calculations and experimental results, establishing a scientific consensus around this explanation. The discovery has fundamentally redefined our understanding of what happens to objects during extended journeys through deep space. Interstellar space contains a constant flux of high-energy particles that continuously bombard any object traveling between star systems. Over millions of years, this bombardment gradually alters the chemical composition and internal structure of icy bodies, creating hidden reservoirs of volatile compounds that can be released when the object encounters stellar radiation. The implications extend far beyond Oumuamua itself. Astronomers now recognize that many objects previously classified as asteroids may actually be hydrogen outgassing bodies that lack visible tails. These objects, dubbed dark comets, represent an entirely new category of solar system inhabitants that bridge the gap between traditional comets and asteroids. The realization that cosmic ray processing can create such objects has led to systematic surveys searching for additional examples of non-gravitational acceleration in asteroid populations. The breakthrough has validated the dark comet hypothesis and prompted major revisions to astronomy textbooks. Educational materials now include discussions of hydrogen outgassing as a normal process affecting interstellar objects, and the mechanisms of cosmic ray processing have become standard topics in planetary science courses. The discovery demonstrates how objects can exhibit comet-like behavior without displaying traditional cometary characteristics, expanding our definition of what constitutes a comet: the hydrogen outgassing. Explanation represents more than just a solution to one object's mysterious behavior. It reveals a previously unknown process that shapes the evolution of icy bodies throughout their cosmic journeys, connecting interstellar chemistry to solar system dynamics in ways that scientists are only beginning to explore. With this mystery solved, astronomers turn their attention to cataloging the full scope of interstellar traffic passing through our region of space, our new cosmic neighborhood census. The systematic analysis of these confirmed detections has revealed we live in a cosmic environment far more active than astronomers anticipated. The Vera C. Rubin Observatory's projected 15 interstellar objects over the coming decade represent just the beginning of a comprehensive census that will fundamentally reshape our understanding of galactic material flows. Each confirmed visitor carries distinct signatures that reveal their origins and histories, representing a vast population of wandering materials that connect star systems across the galaxy in ways we never understood before. The cataloged objects show remarkable diversity in both composition and structure. Some visitors appear nearly pristine, with chemical signatures matching theoretical predictions for materials formed in the outer regions of distant planetary systems. These pristine objects contain high concentrations of water, ice mixed with simple organic compounds, suggesting they originated in cold environments far from their parent stars. Their surfaces show minimal thermal processing, indicating they escaped their home systems without experiencing significant heating events. Other detected objects display clear evidence of thermal processing and chemical alteration. These processed visitors contain complex mineral assemblages that form only under high-temperature conditions, suggesting they originated much closer to their parent stars before ejection. Some show spectroscopic evidence of metal-rich composition similar to terrestrial planets, while others contain exotic silicate minerals that form only in specific stellar environments. The thermal processing creates distinct chemical fingerprints that allow astronomers to reconstruct the conditions these objects experienced before their interstellar journeys. Each visitor tells a unique story through its chemical composition and physical characteristics. Objects with high metal content likely originated in the inner regions of mature planetary systems, where rocky planets and asteroids concentrate the heavier elements produced by stellar nucleosynthesis. Those rich in volatile compounds probably formed in the outer reaches of younger systems, where water and organic materials remain stable in solid form. Size distribution and rotation rates provide additional clues about the violent ejection events that launched these objects into interstellar space. The detection of objects from different stellar populations has revealed fundamental patterns in galactic structure and evolution. Roughly 30% of catalog visitors contain chemical signatures characteristic of population 1 stars, young, metal-rich stars similar to our Sun that formed recently in the galaxy's disk. These objects carry high concentrations of heavy elements produced by multiple generations of stellar nucleosynthesis, reflecting the enriched interstellar medium from which their parent systems form. A smaller fraction of visitors shows chemical patterns consistent with the population 2 stellar environments, older metal-poor systems that formed when the galaxy contained fewer heavy elements. These ancient travelers contain primarily hydrogen, helium, and light elements with minimal concentrations of metals compared to objects from younger stellar populations. Their compositions provide direct samples of materials from the early galaxy, offering insights into conditions during the first billion years after galactic formation. The most intriguing category includes objects that appear to originate from active star-forming regions. These visitors contain fresh organic compounds and unusual isotopic ratios that match theoretical predictions for materials forming in stellar nurseries. The presence of complex organic molecules suggests these objects formed in environments rich in the raw materials for life, where energetic processes create sophisticated chemical networks. Some contain isotopic signatures of short-lived radioactive elements that decay rapidly, indicating they left their formation sites within the past few million years. Ancient system refugees represent another distinct population, characterized by heavily processed compositions and evidence of multiple thermal cycles. These objects likely orbited their parent stars for billions of years before gravitational encounters or stellar evolution events interstellar space. Their compositions reflect extended exposure to stellar radiation and repeated heating cycles that altered their original chemical makeup. Some show signs of aqueous alteration, suggesting they contained liquid water at some point during their histories. The compositional diversity challenges fundamental assumptions about how planetary systems form and evolve. Traditional models predicted relatively uniform compositions within individual systems, with gradual variations based on distance from the central star. The interstellar visitor population reveals much greater complexity, with objects from single systems displaying wide ranges of compositions and processing histories. This suggests planetary formation involves more chaotic processes than previously recognized, with frequent collisions, migrations, and ejection events redistributing materials throughout developing systems. Trajectory analysis has enabled astronomers to trace many objects backward through space, identifying potential source systems across a significant portion of the galaxy. The most detailed reconstructions account for the gravitational influence of nearby stars, the galaxy's rotating structure, and perturbations from massive objects encountered during million-year journeys. These calculations point to source regions within roughly 1,000 light-years of our solar system, though some objects display trajectories suggesting much more distant origins. Several visitors show clear connections to specific stellar systems identified through precise trajectory reconstructions. The closest matches involve objects whose calculated arrival vectors point directly toward nearby star-forming regions or stellar associations. In some cases, the timing of departure matches known stellar evolution events or planetary system formation timescales in the candidate source systems. These connections provide the first direct evidence linking specific interstellar objects to their probable origins. Coordinated alert systems now enable real-time follow-up observations across multiple observatories worldwide, ensuring no potential interstellar visitor escapes detailed study. The discovery of systematic material flows between different types of stellar environments suggests the galaxy operates as an integrated chemical system. Young, active stars contribute fresh organic compounds and volatile materials to the interstellar population, while older systems provide processed heavy elements and complex minerals. This continuous exchange redistributes the products of stellar nucleosynthesis and planetary formation across vast distances, mixing materials from diverse environments throughout galactic history. The realization that planetary building blocks have been continuously redistributed throughout galactic evolution fundamentally changes our understanding of how solar systems form within the broader galactic context. Yet among all these diverse visitors, one category has remained completely hidden until recently, masquerading as something entirely different: the dark comet revolution. The hydrogen outgassing mechanism that explained Oumuamua's behavior opened the door to recognizing an entirely new class of cosmic objects. These objects, now called dark comets, represent a fundamental category that astronomers had never recognized before. Unlike traditional comets that display bright tails and visible comas when approaching the sun, dark comets exhibit subtle acceleration without any observable outgassing signatures. This invisible behavior allowed them to masquerade as asteroids for decades while secretly operating under forces that scientists couldn't explain. Subsequent surveys found dozens of solar system asteroids exhibiting slight non-gravitational acceleration, indicating hydrogen-driven outgassing without visible tails. The objects ranged in size from just 3 meters across to several tens of meters in diameter, with all displaying the characteristic acceleration signatures that distinguish dark comets from purely gravitational bodies. These accelerations followed patterns similar to Oumuamua's behavior, suggesting they operated through the same hydrogen outgassing mechanism that had puzzled scientists for years. Dark comets possess several key characteristics that separate them from both traditional comets and asteroids. They contain significant amounts of water ice mixed with other volatile compound, but lack the dust content that creates visible tails in normal comets. when solar heating triggers the release of trapped hydrogen gas. Rates. The process occurs at rates too low to produce detectable dust clouds or bright comas. Their surfaces appear dark and unremarkable in telescopic observations, showing reflectivity patterns similar to carbonaceous asteroids. The acceleration they experience typically measures only a few centimeters per second squared, requiring precise orbital tracking over extended periods to detect. These objects have been hiding in plain sight within near-Earth object catalogs for decades. Space. Surveillance programs designed to track potentially hazardous asteroids have been observing and cataloging dark comets without recognizing their true nature. The small accelerations they produced appeared as minor orbital perturbations that astronomers attributed to measurement errors or unmodeled gravitational effects. Only after Oumuamua demonstrated that such accelerations could result from outgassing invisible gases did researchers realize they had been misclassifying an entire population of objects. The reclassification of near-Earth objects has forced a comprehensive review of existing catalogs and databases. Objects previously considered purely asteroidal now require detailed analysis to determine whether they exhibit dark comet characteristics. This reclassification process involves examining decades of orbital data to identify subtle acceleration patterns that might have been overlooked. The effort has revealed that dark comets represent a significant fraction of the small body population, with implications for understanding the true diversity of objects in our cosmic neighborhood. The role of dark comets in early solar system evolution appears much more significant than previously recognized. These objects likely represent a primordial population that formed during the initial stages of planetary accretion when the solar nebula contained abundant water ice and organic compounds. Their survival in the inner solar system suggests they avoided the most violent phases of planetary formation, preserving materials from the earliest epochs of solar system history. The hydrogen trapped within their ice matrices provides a record of cosmic ray exposure over millions of years, offering insights into long-term space weathering processes. Dark comets may have played a crucial role in delivering water and organic compounds to the terrestrial planets during the late heavy bombardment period. Their ability to approach the inner solar system while retaining significant volatile inventories makes them efficient delivery vehicles for life-essential materials. Unlike traditional comets, which lose most of their volatiles during repeated solar encounters, dark comets can maintain their water content through multiple orbits, potentially providing sustained input of materials to planetary surfaces over extended periods. The distribution of dark comets throughout the solar system suggests they originated from multiple source regions with different formation conditions. Some appear to have formed in the outer regions of the solar nebula, where water ice remained stable during planetary accretion. Others show chemical signatures indicating formation closer to the sun, followed by migration to cooler regions where they acquired their volatile content. This diversity in formation histories provides insights into the dynamic processes that shaped the early solar system and distributed materials throughout the planetary region. Recent spectroscopic observations have revealed that dark comets contain complex organic compounds similar to those found in carbonaceous meteorites. These organic materials form through chemical processes operating in the cold, radiation-rich environment of the outer solar system. The preservation of these compounds within dark comet interiors suggests they could serve as repositories of prebiotic chemistry, potentially carrying the molecular building blocks necessary for life's emergence. The discovery that dark comets may represent one of the most common object types in the galaxy has transformed our understanding of interstellar populations. If the solar system's dark comet population reflects typical conditions around other stars, then these objects constitute a vast reservoir of materials flowing between stellar systems. The realization that most interstellar visitors might be dark comets rather than traditional asteroids or comets changes how we interpret observations of objects from other star systems and influences our estimates of material exchange rates throughout the galaxy. The implications extend beyond individual objects to encompass the entire structure of planetary systems. Dark comets represent a transitional category that bridges the gap between asteroids and comets, suggesting that the traditional binary classification system requires fundamental revision. Their existence demonstrates that the solar system contains a rich diversity of object types with complex formation and evolution, histories that continue to shape the contemporary space environment. The recognition of dark comets as a distinct class has fundamentally changed how astronomers approach the detection and characterization of small solar system bodies. With this new understanding of what to look for, the challenge now lies in developing the technological capabilities to spot these elusive advanced detection revolution. The Vera C. Rubin Observatory's 3.2 gigapixel survey camera and sophisticated AI pipeline now flag interstellar contenders in real time, providing months of advance warning that gives scientists unprecedented opportunities to study these fleeting visitors. This technological leap has eliminated the frustrating situation where astronomers discovered interstellar objects only after they had already passed their closest approach to the sun and begun their journey back into the void. The observatory's massive improvements in telescope sensitivity, data processing speed, and automated survey capabilities have revolutionized detection networks. Modern wide-field survey telescopes scan enormous portions of the sky each night, capturing images of millions of objects and processing the data instantly to identify moving targets. These systems operate continuously, building comprehensive catalogs of everything visible in their field of view and tracking changes over time with remarkable precision. During its 10-year observational campaign, the Rubin Observatory will track more than 5 million asteroid belt objects, 300,000 Jupiter Trojans, 100,000 near-Earth objects, and more than 40,000 Kuiper belt objects. Among these detections, astronomers estimate the observatory will identify approximately 15 interstellar objects, representing a substantial increase in detection rates compared to previous surveys. This dramatic improvement in discovery potential allows scientists to study much larger samples of interstellar visitors and understand their population characteristics with statistical significance. Artificial intelligence algorithms have revolutionized trajectory prediction and identification of optimal observation windows. Machine learning techniques including random forests, stochastic gradient descent, gradient boosting machines, and neural networks process tracklet data from survey telescopes to classify potential interstellar objects among the millions of solar system bodies detected each night. These sophisticated programs analyze vast data sets to identify subtle patterns in object motion that human observers might miss, predicting future positions of fast-moving objects with remarkable accuracy that enables observation planning weeks or months in advance. Global coordination systems ensure continuous tracking as these objects traverse the solar system. When artificial intelligence identifies a potential interstellar visitor, automated alert systems immediately notify observatories worldwide. This rapid communication allows facilities across different continents to coordinate their observations, ensuring continuous monitoring as Earth's rotation carries individual telescopes out of viewing range. The coordination extends beyond simple position measurements to include spectroscopic observations, photometric monitoring, and specialized studies requiring different instrument types. Space-based telescopes have eliminated atmospheric interference that plagued ground-based detection efforts for decades. The James Webb Space Telescope provides unprecedented infrared sensitivity that allows astronomers to detect heat emitted by interstellar objects and infer their surface temperatures and areas based on their distances from the Sun. The telescope tracks visitor trajectories with exceptional precision, providing orbital data accurate enough to reconstruct their journeys through interstellar space without atmospheric turbulence, weather conditions, or light pollution limiting observation quality. Amateur astronomers contribute significantly to discoveries through citizen science programs that harness the collective power of thousands of dedicated observers. These programs provide sophisticated software tools allowing amateur astronomers to analyze survey data and identify potential discoveries that automated systems might overlook. The distributed nature of amateur observation networks provides geographic coverage complementing professional facilities, ensuring interesting objects receive continuous monitoring regardless of their sky position. Specialized instruments designed specifically for interstellar visitor characterization incorporate features optimized for studying objects traveling at hyperbolic velocities through the solar system. These include high-speed tracking systems that follow rapidly moving targets, sensitive spectrometers analyzing chemical composition of faint objects, and photometric systems measuring brightness variations with extreme precision. The instruments provide data quality sufficient to distinguish between different interstellar visitor types and determine their physical properties with unprecedented detail. Real-time alert systems enable rapid mission planning, with the global astronomy community mobilizing within hours of potential discoveries. These automated networks distribute information instantly to observatories, universities, and research institutions worldwide, enabling rapid response campaigns that maximize scientific return from each detection. Alert systems include detailed orbital predictions, brightness estimates, and recommendations for optimal observation strategies, allowing facilities to begin productive observations immediately without lengthy planning phases. The combination of ground-based and space-based detection capabilities provides comprehensive coverage, ensuring no significant interstellar visitor escapes notice. Ground-based wide-field surveys provide initial detection and rough orbital determination, while space-based telescopes contribute precise astrometry and detailed physical characterization. This multi-platform approach compensates for individual facility limitations and provides redundant coverage, guarding against equipment failures or weather disruptions. Advanced computing systems process terabytes of image data each night, identifying moving objects, measuring their positions and brightnesses, and updating orbital solutions in real time. These systems incorporate sophisticated algorithms distinguishing between solar system objects, interstellar visitors, and instrumental artifacts with remarkable reliability. Quality control systems ensure potential discoveries receive immediate verification through independent observations, with multiple telescopes confirming each detection using different instruments and observing techniques. The detection revolution has fundamentally altered interstellar object science timelines. Where previous discoveries provided only days or weeks of observation opportunities, current systems offer months of advance warning, enabling comprehensive study campaigns. This extended timeline allows scientists to coordinate observations across multiple wavelengths, plan specialized experiments, and consider rapid response spacecraft missions to intercept the most interesting visitors. The transformation represents more than incremental improvement in existing capabilities. It marks the beginning of a new era where interstellar objects become accessible targets for detailed scientific investigation rather than fleeting glimpses of the unknown. With this technological foundation in place, astronomers can now conduct systematic comparisons between different visitors, revealing patterns that were impossible to discern from single object studies. Comparative analysis with new visitors. The wealth of comparative data now available has transformed our understanding of these cosmic wanderers completely. When 2I Borisov arrived in 2019 and behaved like a garden-variety comet, confirming that Oumuamua was the true oddball, astronomers finally gained the context needed to appreciate just how extraordinary their first interstellar visitor had been. Instead of another puzzle similar to Oumuamua's anomalous characteristics, they found a completely conventional comet that behaved exactly as theoretical models predicted. 2I Borisov displayed a prominent comet and tail, clear signs of outgassing activity, and predictable orbital mechanics that followed established comet physics. The object's spectroscopic signature revealed familiar compounds including water vapor, carbon monoxide, and various organic molecules. These observations confirmed that planetary formation processes around other stars produce materials similar to those found in our own solar system. The conventional nature of 2I Borisov validated decades of theoretical work about interstellar object populations, proving that most visitors from other star systems would indeed resemble familiar comets. The early detection of 2I Borisov provided crucial advantages that Oumuamua observations lacked. Astronomers spotted 2I Borisov while it was still approaching the inner solar system, allowing months of detailed study before, during, and after its closest approach to the Sun. This extended observation period enabled comprehensive analysis of the object's composition, structure, and behavior throughout its solar encounter. The timing contrast highlighted how much scientific opportunity had been lost with Oumuamua, which was discovered only after it had already passed the closest approach and begun its journey back to interstellar space. Modern surveys reveal visitors range from active comets to completely inert asteroids, highlighting Oumuamua's place at one extreme of this spectrum. Some objects display typical comet behavior similar to 2I Borisov, developing bright comas and tails that allow detailed spectroscopic analysis of their compositions. Others exhibit more subtle activity, showing minimal outgassing that creates faint halos detectable only with sensitive instruments. A third category includes objects that appear completely inert, showing no signs of volatile activity despite their presumed icy compositions. Each new discovery has refined our understanding of Oumuamua's unique properties through direct comparison. Objects with similar sizes and compositions to Oumuamua behave in predictable ways when they approach the sun, developing the expected cometary features that Oumuamua conspicuously lacked. These comparisons have strengthened the case that Oumuamua's invisible hydrogen outgassing represents a genuinely novel mechanism rather than a misunderstood version of normal comet behavior. The consistent pattern of conventional behavior among other visitors makes Oumuamua's anomalous acceleration even more significant. Several interstellar objects discovered in recent years share Oumuamua's mysterious acceleration characteristics, providing crucial validation for the hydrogen outgassing theory. These objects show small but measurable non-gravitational forces that affect their trajectories without producing visible outgassing signatures. The acceleration patterns match theoretical predictions for hydrogen release from cosmic ray-processed ice, supporting the conclusion that this mechanism operates commonly among interstellar visitors. The discovery of multiple objects exhibiting similar behavior has transformed Oumuamua from a singular anomaly into the first recognized example of dark comets. Compositional analysis of newer interstellar visitors has strongly supported theories about Oumuamua's makeup and origin. Objects with spectroscopic signatures indicating high water ice content consistently display the type of subtle acceleration that characterizes dark comets. Those with rocky or metal-rich compositions follow purely gravitational trajectories without any non-gravitational forces. This correlation between composition and acceleration behavior validates the hypothesis that Oumuamua contains significant amounts of water ice, despite its lack of visible cometary activity. The size distribution observed across different interstellar objects reveals patterns that help explain Oumuamua's unusual characteristics. Smaller objects tend to exhibit more pronounced acceleration effects relative to their masses, while larger visitors show less dramatic non-gravitational forces. This size dependence matches theoretical predictions for surface area to volume ratios affecting outgassing rates. Oumuamua's relatively small size and elongated shape maximized its surface area exposure to solar heating, potentially enhancing the hydrogen release that produced its mysterious acceleration. Studying multiple interstellar visitors has revealed common formation and ejection mechanisms that operate throughout the galaxy. Most objects show compositional signatures consistent with formation in the outer regions of planetary systems, where water ice and organic compounds remain stable during planetary accretion. The ejection process appears to involve gravitational encounters with massive planets or stellar companions that impart sufficient energy to escape their parent systems. These mechanisms produce populations of wandering objects with predictable characteristics that help astronomers understand galactic-scale material transport. The orbital dynamics that distinguish different types of interstellar travelers reflect their diverse origins and journey histories. Objects arriving from nearby star systems follow relatively direct trajectories with moderate hyperbolic excess velocities, while those from more distant sources display higher speeds and more extreme orbital inclinations. Some visitors show signs of gravitational perturbations from massive objects encountered during their interstellar journeys, creating complex orbital signatures that encode information about galactic structure and stellar populations. The comparative approach has fundamentally transformed Oumuamua from an inexplicable anomaly into a recognized prototype of dark comet behavior. The discovery of numerous objects sharing similar characteristics has established that Oumuamua represents the first identified member of an important class of cosmic objects rather than a unique mystery. This reclassification has profound implications for understanding material transport between star systems and the role of dark comets in distributing volatiles throughout the galaxy. The systematic study of interstellar visitor populations has also revealed selection effects that initially biased our understanding of these objects. Early detection capabilities favored the discovery of larger, brighter objects with conventional comet behavior, while smaller or less active visitors remained undetected. Improved survey techniques now identify the full spectrum of interstellar object types, providing a more complete picture of the populations flowing between star systems. With this comprehensive understanding of what to expect from future visitors, the scientific community has begun developing ambitious plans to study these objects in ways that seemed impossible just a few years ago. Mission updates and interception plans. The prospect of actually reaching an interstellar visitor during its passage through our solar system has shifted from science fiction to engineering reality. Multiple space agencies now have concrete missions in development specifically designed to intercept these cosmic wanderers. These aren't theoretical proposals or distant dreams, but funded programs with launch dates, hardware and construction, and international partnerships already established. ESA's Comet Interceptor mission represents the most advanced interstellar visitor encounter program currently in development. Scheduled to launch in 2029, this mission employs a revolutionary wait and intercept strategy that positions spacecraft at strategic locations before targets are even identified. The mission comprises 3 separate spacecraft that will travel to an as-yet undiscovered target and perform simultaneous observations from multiple points to create a 3-dimensional profile of a dynamically new object containing unprocessed material from the dawn of the solar system. The Comet Interceptor will be delivered to the Sun, Earth Lagrange point L2, positioned 1.5 million kilometers behind Earth as viewed from the Sun, where it will remain staged until astronomers identify a suitable target. From there, it will journey onward to its target using its own propulsion system. This staging approach eliminates the traditional constraint of having to design, build, and launch a mission after discovering a target object. Instead, the spacecraft wait in position, ready to respond immediately when astronomers identify a suitable interstellar visitor approaching the inner solar system. Mission planning strategies have evolved dramatically to capitalize on improved detection capabilities that provide months rather than days of advance warning. The extended timeline allows mission controllers to calculate optimal intercept trajectories, coordinate international observation campaigns, and modify spacecraft operations to maximize scientific return. Ground-based telescopes provide continuous tracking data that enables precise navigation updates during the approach phase, while space-based observatories contribute detailed characterization information that helps optimize instrument settings and observation sequences. The technical challenges of intercepting objects traveling at interstellar velocities require solutions that push current engineering capabilities to their limits. Any spacecraft attempting an interstellar object encounter must achieve extremely high speeds while maintaining precise navigation accuracy over millions of kilometers. The mission will need to be capable of an acceleration of 3.0 kilometers per second, establish a minimum flyby altitude of 400 kilometers, intercept the object within 3 astronomical units of the Sun, and achieve a flyby velocity of 100 kilometers per second, according to detailed engineering analyses. Revolutionary propulsion technologies are making previously impossible missions feasible through innovations in solar sail design and laser-assisted acceleration. Next-generation solar sail spacecraft use lasers directed at lightweight, reflective sails to reach unprecedented speeds without requiring heavy fuel tanks that would make rapid response missions prohibitively expensive. These systems offer nimble and cost-effective solutions compared to nuclear propulsion or other exotic technologies that require years of development and testing before deployment. The speed and unpredictable nature of interstellar object encounters necessitate spacecraft capable of making autonomous decisions without ground control intervention. Hiroyasu Tsukamoto has developed Neural Rendezvous, a deep learning-driven guidance and control framework designed to autonomously encounter these extremely fast-moving objects. The system employs contraction theory for data-driven nonlinear control systems, providing stability in complex situations that change nonlinearly over time during high-speed encounters. International collaboration forms the foundation of successful interstellar visitor missions, requiring coordination between space agencies, ground-based observatories and research institutions across multiple continents. The global nature of these efforts ensures continuous tracking coverage as Earth's rotation carries individual facilities in and out of optimal viewing positions. Standardized communication protocols allow real-time sharing of trajectory updates, composition data, and operational status information between participating organizations. Scientific instruments specifically developed for high-speed interstellar encounters incorporate design features optimized for the unique conditions of these missions. The instrument suite draws on heritage from previous missions, including cameras based on systems currently flying on the ExoMars Trace Gas Orbiter, along with dust, fields, and plasma instruments, as well as mass spectrometers similar to those that flew on ESA's Rosetta mission. These instruments must operate reliably during brief encounter windows while collecting data at rates sufficient to characterize rapidly changing conditions. Multiple backup plans and contingency missions stand ready to launch when the next major interstellar visitor approaches our solar system. Project Lyra explores the possibility of reaching Oumuamua using gravitational assist maneuvers with a 2033 launch window requiring 18.2 kilometers per second delta to arrive at the target in 2048, though the technical requirements present significant challenges. The Bridge mission, developed by NASA, aims to intercept objects within 30 days of detection using rapid response spacecraft architectures. These contingency programs ensure that unexpected discoveries don't escape study due to lack of prepared response capabilities. Spacecraft designed for interstellar object encounters must remain functional after years of waiting in storage orbits while maintaining readiness for immediate deployment. The energy systems must avoid degradation during extended dormant periods, while navigation and communication systems require periodic testing and calibration. Advanced thermal management systems protect sensitive instruments from the extreme temperature variations experienced at the L2 Lagrange point and during high-speed solar approaches. The coordination between detection networks and mission control centers has reached levels of sophistication that enable rapid response times measured in hours rather than days or weeks. Automated alert systems immediately notify mission teams when potential targets are identified, while pre-calculated trajectory options allow quick selection of optimal intercept strategies. This streamlined approach maximizes the scientific value extracted from each interstellar visitor encounter. The transformation from reactive discovery missions to proactive interception programs represents a fundamental shift in how humanity approaches the study of interstellar visitors. Rather than scrambling to observe objects after they've already begun leaving the solar system, we now position ourselves to greet these cosmic travelers during their arrival. Yet even the most sophisticated mission hardware depends entirely on the computational power needed to model these objects' complex behaviors and predict their movements with computational breakthroughs and modeling. Advanced simulations and machine learning algorithms have revolutionized our ability to reconstruct Oumuamua's complete billion-year journey through space. Modern computational systems can now model the entire history of interstellar objects with precision that was unimaginable just a few years ago. These simulations track every aspect of an object's experience during its cosmic voyage, from the moment it was ejected from its parent system through millions of years of wandering in the void until it arrived in our solar system. The sophisticated models operating today incorporate factors that previous generations of simulations simply couldn't handle. Galactic radiation bombardment gets modeled at the molecular level, tracking how high-energy cosmic rays penetrate through layers of ice and rock to create chemical changes deep within the object's interior. Stellar encounters during the interstellar journey receive detailed treatment, with simulations calculating how close approaches to other stars affected the object's trajectory and internal heating. The models even account for the gradual accumulation of interstellar dust and gas during the journey, showing how these materials alter the object's surface composition and thermal properties over millions of years. Internal evolution processes now receive unprecedented computational attention through models that simulate the slow transformation of materials during extended space exposure. The simulations track how cosmic ray bombardment breaks apart water molecules to create hydrogen gas pockets, how temperature cycling causes structural changes in the ice matrix, and how radiation processing creates new chemical compounds that didn't exist when the object first left its parent system. These internal changes occur gradually over timescales measured in millions of years, requiring computational models that can accurately represent processes operating across vastly different temporal scales. Machine learning algorithms have revolutionized the identification of patterns in interstellar object behavior that human analysts completely missed during decades of previous research. These artificial intelligence systems process vast databases of orbital observations, brightness measurements, and spectroscopic data to identify subtle correlations that reveal the underlying physics governing interstellar object evolution. The algorithms excel at recognizing complex, multidimensional patterns in datasets containing millions of individual measurements, uncovering relationships between object properties that would require human researchers decades to discover through traditional analysis methods. Recent studies have demonstrated that machine learning approaches, particularly gradient boosting machines and random forest algorithms, significantly outperform traditional detection methods in distinguishing interstellar objects from the millions of solar system bodies observed by survey telescopes. These algorithms process the unique motion characteristics of interstellar visitors, identifying the subtle signatures that distinguish hyperbolic trajectories from the elliptical orbits of solar system natives. The automated identification process not only accelerates discovery rates, but also improves the reliability and consistency of detections by eliminating human bias and fatigue factors that affected earlier search efforts. The integration of machine learning capabilities into the Vera C. Rubin Observatory's data processing pipeline represents a quantum leap in interstellar object science. The observatory's legacy survey of space and time generate enormous datasets containing observations of millions of objects, requiring automated systems capable of identifying the rare interstellar visitors hidden among the vast population of asteroids and comets. Machine learning algorithms trained on simulated LSST data have already demonstrated their ability to classify interstellar object tracklets with accuracy rates exceeding 95%, ensuring that virtually no visitors escape detection during their passage through the inner solar system. The computational models have dramatically refined estimates of Oumuamua, the original composition and structure, before it began its interstellar journey. By working backward from the observed properties and accounting for millions of years of space weathering effects, the simulations reconstruct what the object looked like when it first left its parent system. The models suggest Oumuamua originally contained approximately 60% water ice mixed with rocky materials and organic compounds, very similar to comets observed in our outer solar system. The current dry, processed appearance results from extensive modification during the long journey through interstellar space. Predictive models now forecast the arrival of future interstellar visitors with accuracy that enables advanced mission planning and resource allocation. These forecasting systems integrate data from multiple survey telescopes with galactic dynamics models to predict when and where new interstellar objects will appear. The predictions include estimates of object sizes, compositions, and optimal observation windows that allow astronomers to prepare specialized instruments and coordinate international observation campaigns months before visitors become detectable. The Vera C. Rubin Observatory is expected to detect between 1 and 70 interstellar objects annually based on these predictive models. The computational breakthroughs directly inform the design of future detection and intercept missions by providing detailed specifications for the instruments and spacecraft systems required to study these objects effectively. Mission planners use the simulation results to determine optimal spacecraft trajectories, instrument sensitivity requirements, and operational timelines for successful encounters. The models reveal which types of measurements provide the most scientific value during brief flyby encounters, allowing engineers to prioritize instrument capabilities and data storage systems accordingly. The transformation of Oumuamua from an inexplicable mystery into a well-understood cosmic traveler demonstrates the power of modern computational approaches to solve previously intractable scientific problems. The combination of advanced simulation capabilities and machine learning pattern recognition has confirmed that hydrogen outgassing explains the object's acceleration without requiring exotic physics. These computational tools have eliminated the need for extraordinary explanations by revealing how natural physical processes operating over cosmic timescales can produce the unusual characteristics that initially baffled astronomers. Yet despite this comprehensive understanding, one fundamental question about Oumuamua's nature has continued to generate intense scientific debate. The alien technology debate settled. The comprehensive scientific analysis has definitively resolved whether Oumuamua represented alien technology. After years of investigation and debate, the evidence overwhelmingly supports a natural origin for this mysterious object. The resolution comes not from dismissing the alien possibility without consideration, but from accumulating such compelling natural explanations that exotic alternatives become unnecessary. The specific evidence ruling out artificial construction centers on Oumuamua's physical properties and behavior patterns that align perfectly with natural cosmic processes. High-resolution observations during its solar system passage revealed an irregular rocky surface with no signs of manufactured components, antenna arrays, or other technological features that would be expected from an interstellar probe. The object's surface shows the characteristic reddish coloration that develops on asteroids and comets exposed to cosmic radiation over millions of years. This reddening occurs through well-understood chemical processes where high-energy particles break down organic compounds and create iron oxide minerals on exposed surfaces. No known artificial materials would develop this specific coloration pattern through space weathering processes. The object's tumbling rotation pattern also differs significantly from the controlled orientation that would characterize a functional spacecraft designed for interstellar travel. Artificial objects maintaining specific orientations for communication or navigation purposes would exhibit stable rotation patterns, not the chaotic tumbling observed in Oumuamua. The irregular shape itself, while initially puzzling, matches theoretical predictions for objects formed through tidal fragmentation events where volatile-rich bodies pass too close to their parent stars and shatter into elongated fragments. The discovery of Oumuamua's acceleration mechanism through hydrogen outgassing represents the most compelling natural explanation for its previously inexplicable behavior. This process operates through cosmic ray bombardment, creating hydrogen pockets within water ice over millions of years, followed by controlled gas release when heated by solar radiation. The mechanism functions through established physics principles without requiring any exotic technologies or unknown physical laws. Laboratory experiments have successfully replicated this hydrogen trapping and release process, confirming its viability as a natural phenomenon that can produce the observed acceleration without visible outgassing signatures. The identification of similar acceleration behavior in multiple interstellar objects has eliminated the need for exotic explanations by demonstrating that Oumuamua's characteristics represent normal variations within natural populations. Dozens of objects discovered since 2017 exhibit comparable non-gravitational acceleration without visible cometary activity, proving that this behavior occurs commonly among interstellar visitors. The consistent pattern across multiple objects strongly supports natural mechanisms rather than technological intervention, as it would be highly unlikely for numerous alien artifacts to employ identical propulsion systems while displaying no other technological signatures. The alien hypothesis served valuable scientific purposes despite ultimately proving incorrect. The speculation prompted astronomers to examine Oumuamua's properties with unprecedented thoroughness, leading to discoveries about interstellar object populations that might otherwise have taken decades to uncover. The debate forced scientists to consider all possible explanations systematically, improving the rigor of analysis methods and expanding the range of phenomena considered during object characterization. The experience has fundamentally improved methods for distinguishing natural from artificial objects encountered in space. Current criteria for evaluating potential technosignatures incorporate lessons learned from the Oumuamua investigation. Objects must display clear evidence of artificial construction, controlled orientation, or trajectory modifications, emission of structured signals, or other unambiguous technological signatures before being classified as potentially artificial. The criteria require multiple independent lines of evidence rather than relying on single anomalous characteristics that could result from natural processes. This approach prevents premature conclusions while maintaining appropriate scientific skepticism about extraordinary claims. The natural explanation for Oumuamua's behavior proves far more fascinating than any artificial alternative could provide. The object represents a natural laboratory for studying cosmic ray processing, interstellar chemistry, and galactic material transport operating over millions of years. The hydrogen outgassing mechanism reveals previously unknown processes that shape objects during their journeys between star systems, opening new fields of research into interstellar object evolution. The discovery that seemingly impossible acceleration can result from subtle natural processes demonstrates the incredible sophistication of cosmic chemistry operating on astronomical timescales. The resolution of this debate has established new standards for evaluating unusual cosmic discoveries while maintaining appropriate openness to extraordinary possibilities. The progression from mystery to understanding illustrates the power of combining observational data, theoretical modeling, laboratory experiments, and computational analysis to solve complex problems. The scientific method has triumphed by demonstrating how systematic analysis can resolve apparently inexplicable phenomena through natural explanations. The comprehensive evidence supporting natural explanations has effectively closed this chapter of speculation while revealing something far more significant. Oumuamua has opened our eyes to the remarkable natural processes that operate throughout the galaxy, connecting star systems through constant flows of materials that have been reshaping cosmic environments for billions of years. The object's true legacy extends well beyond resolving questions about its own nature, future implications, and cosmic connections. These discoveries have revealed that our solar system exists within a vast network of cosmic highways where materials flow continuously between star systems. The realization that interstellar visitors pass through our region regularly means we participate in a galactic scale exchange that has operated for billions of years, mixing and redistributing the products of stellar evolution throughout the galaxy. Interstellar visitors serve as direct messengers connecting our solar system to the broader galactic community in ways that were previously impossible to study. Each object carries chemical signatures from its parent system, providing samples of materials that formed around other stars under different conditions. These cosmic specimens allow scientists to study planetary formation processes operating throughout the galaxy without requiring interstellar travel. The diversity of compositions found among interstellar visitors reveals that planetary systems form under remarkably varied conditions, producing materials with properties that differ significantly from those found in our solar system. The role these objects play in distributing materials throughout the galaxy operates on scales that dwarf individual stellar lifetimes. Interstellar objects spend millions to billions of years traveling between star systems, during which they accumulate cosmic ray damage and interstellar dust while carrying materials from their origins to distant destinations. This galactic scale recycling process ensures that the products of stellar nucleosynthesis and planetary formation spread throughout the galaxy over cosmic time. Heavy elements produced in the cores of massive stars eventually become incorporated into planets orbiting completely different stellar systems through this continuous material transport mechanism. The potential for interstellar visitors to distribute organic materials and possibly life throughout the galaxy represents one of the most intriguing implications of recent discoveries. Many interstellar objects contain organic compounds and water ice that could preserve biological materials during the harsh journey through interstellar space. The discovery that some visitors originate from the outer regions of planetary systems, where conditions favor the preservation of complex molecules, suggests they could serve as vehicles for transporting the building blocks of life between star systems over geological timescales. Studying interstellar visitors directly informs our search for habitable worlds around other stars by providing ground truth data about the materials available for planet formation in different stellar environments. The compositions of these objects reveal the chemical inventories present in their parent systems, indicating whether conditions existed for the formation of rocky planets with substantial water reservoirs. Objects rich in organic compounds suggest their parent systems contain the raw materials necessary for life, while those dominated by processed minerals indicate different evolutionary pathways that might favor or hinder habitability. Knowledge gained from interstellar object studies influences strategies for detecting and studying exoplanets by providing insights into the materials available for planet formation around different types of stars. The chemical signatures found in interstellar visitors help astronomers interpret spectroscopic observations of exoplanet atmospheres and surfaces. Objects originating from metal-rich stellar environments provide calibration data for understanding how planetary compositions vary with stellar metallicity, while those from metal-poor systems reveal how planets form when heavy elements are scarce. The potential for using interstellar objects as natural laboratories for extreme physics experiments offers unprecedented opportunities to study processes that cannot be replicated on Earth. These objects experience conditions during their interstellar journeys that subject them to cosmic ray bombardment intensities, temperature variations, and timescales impossible to achieve in terrestrial laboratories. The chemical and physical changes they undergo provide insights into material science under extreme conditions and the behavior of matter in interstellar environments. Understanding interstellar visitors helps predict our solar system's future evolution by revealing the long-term processes that shape planetary system architectures throughout the galaxy. The continuous exchange of materials with other star systems means our solar system will gradually lose some of its original inventory while gaining materials from distant sources. This ongoing process will slowly alter the chemical composition of the outer solar system over billions of years, potentially affecting the evolution of environments like Europa or Enceladus. The discovery that interstellar visitors carry information about conditions in their parent systems means we can study stellar environments that would otherwise remain completely inaccessible. These objects serve as time capsules that preserve records of planetary formation processes, stellar evolution events, and galactic chemical evolution operating over enormous spatial and temporal scales. Each visitor provides a unique dataset that contributes to our understanding of how the galaxy has evolved since its formation billions of years ago. The continuous nature of interstellar material transport implies that the galaxy operates as a single, integrated system where events in one stellar system can eventually influence conditions in systems hundreds of light years away. This galactic scale connectivity means that the formation and evolution of a planetary system cannot be understood in isolation, but must be considered within the broader context of galactic evolution. The materials available for planet formation around any given star depend not only on local stellar processes, but also on the history of material exchange with other stellar systems throughout galactic history. Rather than existing in cosmic isolation, our solar system participates in processes that connect it to stellar environments throughout the galaxy. This realization transforms our understanding of planetary formation, the search for life, and the future evolution of our cosmic neighborhood. We are not merely observers of distant stellar systems, but active participants in a galactic community that has been exchanging materials and information for billions of years. What began as a single puzzling object has opened our eyes to an entirely new understanding of how the universe operates. The scientific journey that began with one mysterious visitor has fundamentally transformed our cosmic perspective. Oumuamua's story led to discovering hundreds of interstellar visitors and revealed natural mechanisms for their behaviors, forever changing our view of a richly interconnected galaxy. The hydrogen outgassing mechanism that solved Oumuamua's acceleration mystery has become the foundation for understanding an entire class of dark comets operating throughout our solar system. Advanced detection networks now identify these previously invisible objects regularly, while sophisticated computational models reconstruct their billion-year journeys through space. The Vera C. Rubin Observatory stands ready to detect dozens more interstellar visitors in the coming decade, each carrying unique stories from distant stellar systems. The next interstellar visitor could be